Hello, everyone. Welcome to another section for Stat 1220 Elements of Statistics 1. Okay, so yesterday we did that is section 3.1 and 3.2, which actually talked about sample space events and their probabilities for 3.1 and 3.2. We did that of the intersection, union, and complement. All right, so today on 3.3, we will talk about the conditional probability and independent event. Okay, so when we talk about conditional probability here, we are conditioning one event on the other event, and therefore we want to find what is the probability of this. So given certain information, then what is the probability of that event actually occurring? That is the whole idea of conditional probability. So we will start with the conditional probability and therefore move on to the independent event. Okay, so there is a formula for conditional probability, and there's a word, whenever you hear it, it actually divides two events. So if you have A given B, then if you want to find the probability of that, then it should be probability of A with a slash, then you bring what? Your B. So the given means is the keyword, and that helps us to determine how to find a conditional probability. So as you can see here, we have such here. So this is the given and this is the keyword being used. So if we are to find the probability of A given B, this is how we write it. And there's a formula, rule of conditional probability. So we have it to be probability of A given B to be equal to the probability of A intersection B all over probability of what? B. Okay, so that's what we see. So we will actually apply this formula in solving some kind of questions involving the given situations. Okay, so let's see how it goes. So what is the sample space? So we have a random experiment whereby we rolled a six-sided fair die, and when this happens, we know the sample space involved. So the sample space is what? 1 through to 6. Then we have to find the probability of rolling a 4. Okay, so there's the probability of rolling a 4. So in the sample space, each outcome is equally likely to occur. So the probability of rolling a 4 is 1 over 6. 1 over 6, that's what we see. Now, we are being asked to find the probability of rolling a 4. Now, given that the number is even, so we've been given another event. So here, in case you want to understand it more, you can let your A to be equal to rolling a 4, and your B to be equal to even number. Okay, all right, so rolling a 4 means that we have a set of 4, and B means that an even number in the sample space, we have it to be 2, 4, and 6. Okay, so if you want to apply the formula for conditional probability, then it will be probability of A given B, which is equal to probability of A intersection B all over the probability of what? B. Okay, so you apply this formula, then you're going to get the answer. We know we've already discussed about intersection. It implies that what outcomes are in A as well as in B. Then if you get that outcome, find the probability of that occurring over the probability of what B. That will give you the answer. So that is what we were doing here. Okay, that is what we are doing here. But intuitively, before you solve this, since you know that an even number occurred, we have three even numbers. So what is the probability that 4 is occurring within this even number? Now, we've restricted the space from the S to what? To our number of even numbers. So since you have 2, 4, 3, then the probability that 4 occurs is what? 1 over 3. So that is intuitively. But you use the formula to prove that. So we have it to what? 1 over 3. That is the answer that we have here. Okay, so the same idea was the probability of rolling an even number given that. So 4, okay, so we know that 4 has actually okay. So the probability that we get an even number should be 1. So you can apply the formula. Always you can define your event. So A should be your even number and B should be getting the number 4. You apply it, probability of A given B, then you get the same answer. We're going to get 1 here. Okay, so this is the whole concept of conditional probability. All right, so now we want to apply that idea in a 2 by 2 contingency table. All right, so before we do that, we have to solve some questions for which you know answers to. All right, so first of all, so we have this table and we have the columns and the rows. So the columns are person has HIV, person does not have what? HIV, and we have the rows to be positive and what? Negative. And we have some numbers within them. So these numbers tells us the intersection between what the rows and what the columns. So now, what is the probability that the person does not have HIV? So we go to this column, and how many people do not actually have HIV? So in this column, we are having what? So those that do not have HIV are those people here, and we have the total to be 99500. So you pick this number and divide by the total number of people that you're talking about. That is what? 100,000, right? So this gives you the probability. This gives you the probability. Now, what is the probability that the test is positive and the person does not have HIV? So this brings some kind of intersection. So the person tests positive, so we have this positive here, and the person does not have HIV, so we have this one here, but there are a number of people that actually intersect here, and this is 1990. Then you pick that over the total, and this gives you what? The probability of those that test positive and the person does not have HIV. Okay. And what is the probability that a test is positive or the person does not have HIV? So or means the union. So we are going to define an event. So the event you have test is positive and does not have HIV. So we apply the definition for what? The probability of union. The probability of A union B is equal to probability of A plus probability of B minus their intersection. So probability of A means that we want to find those that have HIV only. So when you go top, so how many people have HIV? So you have it here. So you go to this column, we have 2488. So these are those that test positive for HIV. So, and if you pick that over the total, you get a probability. And those that do not have HIV, how many people do not have HIV? So you have it to be what? 99500 over the total. So this gives you the probability. Now we locate their intersection. What is the intersection? So this is the intersection that we have, 1990 over what? The total. Then we get our probability. But note that we've already calculated it here. We have one here already. We have this here already, and we have this also. We have this also here. So the only part was to calculate was the positive part, the probability of the test positive. Then we are good to go. Okay. So you do your calculation, then you should get this answer. Now we are coming to the given situations. So this is where the interesting thing, you can apply the formula or you can use this to get your answer straight away. So now we are saying that what is the probability that the test is positive given that the person has HIV? So now we've restricted the 1,000 to some number of what? People that we are interested in. So that is the person has HIV. So this is the column that actually tells us the number of people that actually have HIV. So out of that 100,000, we are interested in this column. We are interested in this figure. That is the 500. Okay. So within this 500, we want to find what is the probability that the test is positive. So who are those that test positive in this 500? We have what? 498. So that gives you the probability. Or you can apply the formula. That is the probability of A given B should be equal to probability of A intersection B all over the probability of what? B. So what is your A and what is your B? You define it. So A is test positive, B has HIV. And since they are intersecting, so who are those that test positive and has HIV? So we have them to be test positive and has HIV. So the probability of that is 498 over what? 100,000. So we have 498 over 100,000 for the top. Then we divide by what is the probability of B. Probability of B are those that has HIV. So how many people has HIV? We have 500 over what? 100,000. So we have 500 all over what? 100,000. So if you solve this, you realize that the denominators will cancel each other, and you're going to have 498 all over 500, just like that. Okay, so this is the approach. So the formula works, and this also what works. So use any of them that best suits you. So we apply the same knowledge here. So given that the test is positive, so we go to those positive column. So this is the positive. So we have total of what? 248. Now we come back to, okay, now who are those that have HIV in this test positive? So we have 498, 498, 498, 498. So that gives us what? The probability. Okay. Now no HIV. Can go to no HIV. So no HIV, we have 99500. And what does the question ask us? So those that test positive in this no HIV. So we come here, we have 199 over 99500. Okay, so that gives us this value that we are looking for. Okay, and so we restrict it, then you'll be good to go. You can actually apply the same idea to the G question. All right. I think you'll be fine. All right, we have another contingency table here. Then we have to solve the same question. So we have to find the probability that a randomly patient has a family. So we have the columns to be developed breast cancer, does not develop breast cancer. Rows are has family history of breast cancer, no family history of breast cancer. And we have numbers in them. We have that. We have what their total as well. Okay, so what are we being asked to find? So we want to find what is the probability that a randomly patient has a family history of breast cancer. So we go to those that have breast cancer. Okay, so we have 103 people over the total, and that gives us what? The probability. So that gives us what? The probability. And given, so we are given a situation that randomly chosen person has a family history of breast cancer. So as a family, so we are restricted to this column. We are restricted to this total. Then what question follows? Find the probability that she develops breast cancer. So who are those in this row that actually has breast cancer? So we have 95 of them. The 95 who had 103. That gives you your probability. Okay. All right. So that is the analogy behind. So you do same for the rest, and I think you should be good to go. All right. So let's try and solve the D. So we have the find the probability that a randomly chosen person has a family history of breast cancer but does not develop breast cancer. Okay, so the but here means the intersection. So you go to those that has family history of breast cancer but does not. So the intersection. So we go to has family history but does not. So we have 8 here. So we pick the 8 over what? The total. That is 185. Then we find what? The probability. Okay. The end here also helps us, so we'll be able to do that. And you have to also find a probability that a randomly chosen patient has a family history of breast cancer, or so we are using the or situation here. So it will be probability of A union B equal to probability of A plus probability of B minus their intersection. So you apply the same idea here. So we have fast family history or developed breast cancer. This equals probability of fast family history. So you have 103 over 185 plus developed breast cancer 135 over 185 minus what their intersection, which is 95 over 185. And you're going to get this answer. You're going to get this answer. So that is how we do it. Okay, so now we are coming to the independence. And okay, so remember from the conditional probability, we actually talked about probability of A given B, which gives us a certain formula. Okay, so the formula that we knew was probability of A given B, which gives us probability of A intersection B all over probability of what B. But we want a situation whereby the probability of A given B equal to probability of what? A. This implies that given B, we have the probability of A given B to be equal to what? Probability of A. This implies that B does not affect what? A. If B exists, still we will still get our answer to be that. But how can we actually get this to be equal to probability of A? That is the whole concept. Or in case if you have probability of B given A, we want it to be equal to probability of what? B. Okay, So this is the whole concept of what you want to develop. So when you talk about two events are independent, then we want to know that, okay, if they exist together, each of them can actually what have no, the other event has no control over what the other. That's the whole concept. So then there's a situation if and only if we could have probability of A given B to equal to probability of A. So let's use this for instance to prove and get to understand what you mean. So by the formula, we know that probability of A given B equal to probability of what A intersection B all over probability of what B. Okay, so how can we get the whole of this to be equal to A? How can we get the whole of this to be equal to probability of A? Then the only thing that can happen is that then the probability of A intersection B should be equal to probability of A times probability of what B all over probability of B, so that B probability of B cancels what the probability of B here, so that we can get probability of what A. Okay, if this happens, then we are saying that probability of A given B equal to 8 if and only if we could have probability of A. If we can have probability of A intersection B equal to probability of A times probability of what B. Okay, so for you to go through this process, we simplify everything to this. If you're able to find that probability of A intersection B equal to probability of A times probability of B, then we are saying that A and B are what? Independent. Independent. That is the whole concept. A and B are what? Independent. Okay. So we are going to use this to determine whether two events are what? Are independent or not. This is what you're going to use to determine. So this implies that you have to find the probabilities of three events. You have A intersection B, probability of A, and probability of B, if you define your event as so. All right, so we have an example here to apply our understanding. But before that, there is something you have to note. Back then we discussed about mutually exclusive or disjoint event. When you talk about disjoint event, we are saying that if you have A intersection B, then we have to let them to be equal to what the null set or the symbol. Okay, but the disjoint such that the probability of A intersection B equals what 0. But when you talk about this independent event, it's different from the mutually exclusive. You want the probability of A intersection B to be equal to the product of their individual probabilities. Okay, that's what you want. Okay. So we have a single fair dice rolled once. Okay, let A, we have A to be 3 and B to be 1, 3, 5. A and B are events A and B independent. So what are you to check? First of all, we have to find their intersection and find the probability of their intersection existing. Then we find the probability of A, find the probability of B. We multiply it together, then we compare. So realize that A intersection B gives us what? 3. Okay, and we have the probability of 3 is 1 over what? 6, because each element in the sample space is equally likely to occur. And the probability of A, what is the probability of A? Probability of A is what? 3. It's 1 over what? 6, because A is just equal to 3, so probability of 3 occurring is 1 over 6, and probability of B occurring is also 3 over what? 6. So this implies that 1 over 6 will never be equal to 1 over 6 times 1 over 3. So if this is not equal to that, then we are saying that A and B are not independent. A and B are not in, because probability of A intersection B is not equal to this. But if you have them to be equal to, then we are saying that A and B are what? Independent, are independent. So always, if you have to check that events are independent, find their intersection, then find the probability of that intersection existing, put the answer there, calculate calculate the probability of their individual what? Event, then multiply them together. Check whether the answer you have at the right is equal to the answer at the left. If they are the same, then they are saying that they are independent. Okay, so let's check some example here. So here we have 16 cars, and four of them are blue, four are yellow, four are green, and four are green, and four are red. So these cars are numbered 1 to 4, okay? And a single card is drawn at random. We define the events A to be the yellow card. So know that we have 4 yellow cards, and we've numbered it 1 to what? 4. So since we don't know the actual values in it, we make A to be equal to y1, y2, y3, and what? Y4. So we have to list the outcomes that comprise A, B, C. So since A is the yellow card, we make it A to be equal to what? Y1 up to Y4. Then B, the number on the card is not 1. So we pick all the 16 cards and we eliminate all the ones. So we have what? B to be this. Then the C is the number on the card is 2 or 4. So we pick all the cards, that is 16, and we pick those that are numbered B2, B4, AB, G2, G4, so on and so forth. So that is be the event C. Okay. Now we have to list the outcomes that comprise A intersection B, B complement, and A union C. So what is in A and as well as in B, that is A intersection B. So we have it to be this y2, y3, y4, and B complement is what is in the sample space, but we can't find it in B. Okay, but remember that we eliminated all the ones in B. So the B complement will be the ones comprising of the ones. All right. That is A union C. So this implies that we are actually adding all the elements in A and C together. But if some of them are repeating, we just write one of it. Okay, so you add A and C together and you're going to get this. We ask ourselves, are B and C mutually exclusive? So this implies that you have to find the intersection between A and what? You have to find the intersection between B and C and check whether it is an empty set. If it is an empty set, then they are what? Mutually what? Exclusive. So you can check A, you can check B and what? C. You can check B and C. So this is my B. This is my B. I'm coming. Oh, and C. So this is also C. Okay, so what elements can we find in B as well as in C? Do we have such? Okay, because we have such, because we can have B2, B2 in. So that alone means that indeed they are not mutually what? Exclusive. Even we find since, so no, the answer is no, because they share what? Some cars in common. They share some cars in common. Okay, so therefore they are not mutually exclusive. They are not mutually exclusive. Okay. Assuming all outcomes are equally likely, so it implies that they have equal what chance of occurring. So you have 16 of them. So if you pick Y1, the probability of Y1 occurring is 1 over 16. We have to find the probability of A complement and what? B union C. So what is the probability of A complement? We can use the complement rule of probability. That is 1 minus probability of A. We know A. We know that we have 4 elements in A and they are all equally likely to occur. So we have 4 over 16 for probability of A. Subtracted from 1, we get what? If you reduce this, you're going to get 12 over 16, but you can reduce it further. Since 4 over 16 gives you 1 over 3, 1 over 4, then subtract 1 over 4 from 1, you could get 3 over 4 or 12 over 16, and that also reduces to 3 over 4. Okay. So this is the answer. And we have to find the probability of B union C. We apply the additive rule, the probability of B plus probability of C minus their intersection. Find the probability. So probability of B, we have 12 elements in it. That is 12 over 16 plus probability of C. We have 8 elements, so 8 over 16 minus the intersection. And you get this answer. Okay. Now we have additional. So suppose that events E and F are independent. This implies that since we have two events here, they are saying that since they are independent, then this exists. It implies that the probability of the probability of what? E intersection F equals to probability of E times probability of what? F. So they are saying that this exists. Okay, they are independent, so this exists. Then we've been given the probability of what? E to be 0.3 and the probability of what? F to be 0.8. Okay. Now, what is the probability of the intersection? So we won't find it. So since this is true, then this is equal to their products. So it implies that probability of E intersection F should be equal to 0.3 times 0.8. Okay, so that is the idea behind. Okay, that is the idea. I've worked it in a rough manner, but that is the whole idea. Then we want to find what is the probability of E or F. So we apply the additive rule. We apply the additive rule here. So this is the first question. What is the probability of E or F? So apply the additive rule and you're good to go. Note that you've already found this already. From the first question, we found this. So apply the additive rule and you're good to go. So let's try to solve this question. About 19% of the population of a large country is nervous around strangers. Okay, so if you pick each individual, the probability that you are afraid of an individual coming into this population is what? Like you are nervous about a stranger coming into the population is what? You are 0.19, that is 19%. Okay, so we pick two of you. Suppose that two of you are randomly selected. This implies that each individual is independent of other. If I pick you and I pick another person, you are independent of the other person. So if you exist together, then the probability that both of you are afraid of or both of you are nervous of a stranger will be the product of your individual probabilities. So we are being asked, what is the probability that both are nervous? So we pick two. We want to find the probability that both are nervous. So that is the intersection. So probability that the first person and the second person and being nervous is 0.19, 0.19. So we multiply them together and that gives us what? This answer. So this implies that if you are not nervous, then it's what? 0.81. 0.81. So we want to also find what is the probability that at least one is nervous around the strangers. Okay, so since we've picked two, so at least means that either the first person or the second person or both. So this implies that we are going to use the idea of what? The additive rule. Or you can also simply work it using the complement rule. So the complement rule says that the probability of at least one is afraid, one is nervous, one is nervous, will be equal to 1 minus the probability that none is what? Nervous. Okay, all right, so you can find the probability of this. So this is 1 minus. So if they are not nervous, then you have to find 1 minus what? 0.81 times what? Another 0.81. So this is the probability that they are not nervous. The answer we get, you put it here. So that was the idea behind this. To get what? Our final answer. Or we can use the additive rule. The additive rule says that, so if you have the first person to be our A and the second person to be our B, then you're going to have the probability of the first person or the second person to be equal to the probability of the first plus probability of the second minus the probability of first and the second. Okay, so this implies that the probability that the first person is nervous is 0.19 plus the second person is also 0.19 minus the intersection. So the intersection is the product of these. So we have 0.19 times 0.19. Okay, so solve this to make sure it's in brackets. So solve this, you're going to get the same answer as the one here. Okay, all of them will give you the same answer. So this is what we actually learned for week 3, and we'll be beginning week 4. That is the week coming. All right. I hope all of you have a nice week as we meet again. All right. Bye bye. Thank you.